Let's create the design of a MEMS microphone. So it has multiple layers. So let me create 3 layers initially. Let's create the rectangle. So I use these coordinates. So if it's out of view, you can just zoom in, zoom out, sorry, so that you can get it. Or I can use this option to zoom to fit, so it fits the geometry. We have created this. Let's have one layer in layer 2. Let's create the anchors. So let's take a mirror image of this. So I've created 2 of them. So let's take a mirror again. Okay. So now we will have 2 more ranges on either side. So let's draw them. So we have created 2 more. Let's mirror this on the other side. So we have created this geometry. Okay, so now let's create one more on the top, similar to what we did just now, but with some perforations. So we've created the geometry, the anchors on either side. So now we'll create one more or 4 more on top and bottom. So let's take the mirror again. First we'll take the mirror on the side. So we've done the top layer. So there are a few more things that we have to do. Is the perforation. So we have saved this file. Let's create the perforations now on the layer 3. Say we create the perforations. Perforations are basically a small holes in the diaphragm. So let's either draw them and then set the dimensions here. So you can choose the position accordingly. Let's make it as some 30 micrometer size. And then we can have them throughout the geometry. So we select this and then we can create an array of this. 10 rows and 10 columns. So in 500 by 500, you can plan accordingly. So there's a slight overspill. So maybe we can try to delete. Something of this sort. So we save. So this is a fill geometry, right? So it's filled geometry. So where do we see a perforation happening? So here we have to perform a Boolean operation to get the perforations. So here we select all of them to create the perforations. Select and then right click, create block. Created something called as perforations. Okay, and now with the selection, if I select one, so I get selected. So now it's complete a block, and with this I make a subtract. So b minus a. B is the selection made in the second, so that's the rectangle, and this a is all the perforation holes. So I click OK. So I get this perforations here. So I save. I'm done with a blueprint. Yeah, once the design is done on blueprint, let's import that file. So we have 3 layers here. Whenever we are simulating design and trying to simulate something with a specific example, especially in the electrostatic simulation, it's always better to have a very good mesh. Okay, so let's first define all of these mesh conditions. So let's do this. So we click on auto remesh. So it takes care of the appropriate and suitable mesh that is required. So let's save this file. Let's define this, modify height. And then we'll add a new level, a blank level above this. and let's retain that height to be 2.5 micrometers. And finally the level 3 retain somewhere around 10 micrometers. So we have these number of layers here. Okay, yeah, so we have level 0, which is on the bottom, level 1, 2 is the blank level, and level 3. Save this and then let's export this to the analysis module. Yeah, we will have the design on thermoelectromechanical module. So let's increase its Z factor to have a better clarity of the device. Let's set the simulation settings. So starting, we do a sensitivity analysis. We will see what is the sensitivity of this device. Select this thermoelectromechanical relaxation, material properties. So here you can check silicon 100 for instance, just applying for this. Then we go to loads, voltage, entity. So we select the top entity. Say we apply let's apply voltage 5 volts, and in the bottom we'll apply 0 volts. Let's fix the boundary conditions. Click OK. Since we are doing electrostatic analysis, we'll have to take care of the electrical mesh. So we apply one phase at the bottom where it makes the electrostatic phase of one of the conductor. So we enter in the factor 2, and we'll have to factor in the layer, the surface below this green entity. So we'll have to disable this for a while and then select the area which is below this entity. So we select here, it gets selected but it doesn't appear, so the green entity comes back, but don't worry, it has taken care of that, but you ensure that it has been selected at the right location. And then once that is done, we'll enable this entity too and then go to mesh, update electrical mesh. We are done, all set. So we'll run the simulation. Yes, we are done with the simulation. So let's check the results. So here we have the displacement, which is maximum in the center. And then we have the capacitance. So here we have the capacitance value 1.29 femtofarads. Okay, so this is the capacitance between the two conductors when there is a potential difference between them. Okay, So now let's repeat or redo the analysis. Now we shall apply the pressure on the face. So we'll apply pressure in the bottom face. So we'll apply 1 Pascal of pressure. So we clean up the analysis and then redo the analysis again. Simulation is complete. So let's look at the displacement. So displacement will be increased because the pressure applied is 1 Pascal, which was not there earlier. So now let's look at the capacitance. So we have this value. So 1.292065. So let's make a note of this. So when we feed in these numbers of capacitance before applying the pressure and after applying the pressure, so this is what we get. So this is how we calculate the sensitivity of this microphone. So the current example that we are trying to run has a sensitivity of 2.82 millivolts per Pascal. Okay, so this is the sensitivity analysis. Okay, let's perform a frequency analysis here. Material properties, silicon 100, let's retain it as it is. So in frequency analysis, generally we don't apply any loads, so we delete all of them. Okay, and then we go to loads, no loads, boundaries are fixed, mesh, let it be as it is. We run the analysis. So we clean up the previous analysis and then run frequency analysis. Okay, the simulation is complete. So here let's see the natural frequency of 3 modes of vibrations. So we get this 3 modes of vibration. So we see mode 1, 2 and 3. Okay, so here we have mode 1, 36.38 kilohertz. Mode 2 is 76 and then mode 3 is also 76. So how do we see these mode vibrations? Go to results, mode animation. Just emphasize on the scaling factor. So we see the modes of vibrations. Okay, I think 10 was too high, I believe. So I think we could have retained 1 itself. So we'll retain it. We'll see it again. So there's the modes of vibration that we have. Okay, so here we can push this to animation file, but I would recommend you to use this option of pushing this to post processor and then create a post processor here and then get a very good graphics. So post process for visualize, open in visualize. That's what we have seen in the basic training examples. So you can repeat that. Okay. So here we have mode 2 and mode 3 as well. Mode 2 of vibrations. So we have mode 2 of vibrations. Let's look at pull-in analysis. So generally, pull-in analysis is done to find out at what voltage the contact happens. So here, let's define this green entity to be a dielectric layer. So we'll define this to be a Si3 and 4 material. So let's apply voltage. So we'll set this to be 0. We set this to be 0 to 15 in the increment of 3. And then since we have checked this box of contact analysis in simulation settings, we have checked it. We'll have to define the contact pair definition. So we set, I think this has got reset back. Contact phase pair, phase A. So our phase A is always the one which will make the contact. So this phase, which is at the bottom, is the phase that will try to make a contact. So we define that to be a phase A, and then we define this to be a rigid body, the phase B, and then we do the complete pair. We will enable them by double click on, and then we check whether it's activated. Yes, it is activated. And we clean up the previous analysis, and then we run the analysis. So this will take a very long time to do the simulation because it has to do for various voltages and with various increments. Pull-in voltage analysis usually takes time. So the simulation is complete. It's taken almost 3 hours on my PC. So generally pull-in voltage analysis takes quite long time. Okay. So let's look at the results. Okay. So here we have a gap of 2.5 micrometers. So I'm not too sure whether the voltage 15 was sufficient, but you can always cross-check with the pull-in voltage formula before giving the input to the software. Okay, so here we see 0.28 micrometers, roughly about 0.3 micrometer displacement. But anyways, the purpose of this simulation is to show you how to plot a pull-in voltage plot. So you can check whether the x-axis is on voltage scale, and you can plot z displacement. So the upward direction shows that it is moving upwards. Okay, so here the displacement is on the upward direction. Okay, so that's why it's showing positive. If the displacement is on the downward direction, it will show in the negative. So the y-axis value will always show in negative if the displacement is in the downward direction. Okay, so here this is how we can get the data. So what we can do is we can get this plot, and then we can copy it and then paste it on the Excel sheet, and then you can plot your graphs. That's one way of doing it. Or else you can use a wave runner, which we will see sometime later about wave runner. Okay, yeah, so this is how we can get the voltage versus displacement plot. So let's look at another plot. Very important plot is voltage versus capacitance. So here we can get this data, capacitance. Click OK. You can see that there is a change in capacitance. There is an increase in capacitance. Okay. So here it's just a negative value does not have any significance. So you can see how the capacitance value keeps changing as it goes closer to the conductor. Yeah, so this is how we can get the data. So from here we can get voltage versus display. From this plot we can get voltage versus capacitance. On the other plot which I showed you earlier, we can get voltage versus displacement. So we can plot displacement versus capacitance. Okay, so this is how we can generate the capacitance plots. Okay, and the pull-in plot. So these are very essential. So why did we do this simulation of pull-in analysis? Because in the electrostatic force of actuation, we generally apply voltage. Okay, when the device is capacitive based, if in the sensitivity is due to capacitance or due to electrostatic force of attraction, we need to know at what voltage the pull-in will happen. Okay, any value which is closer to the pull-in, that is 2/3 of the gap of displacement, we should not apply any voltage which is close to pull-in voltage. Because the reason is these are very sensitive devices. When the voltage increases, there could be a displacement for the input voltage itself. But the problem is the displacement should not be due to the voltage applied. So here we are looking at pressure, the acoustic pressure. So this is a microphone. So when we are looking as acoustic pressure as an input, if there is a displacement due to voltage, then it's a wrong signal. Okay, so but we require voltage to be applied for measuring the capacitance. So we need to find a safe zone of voltage where we can get the capacitance as well, and electrostatic force of attraction is very minimal. So I think up to 15 volts is still okay. It is still not met the 2/3 of the gap. The gap is 2.5 micrometers. Okay, so I think 15 volts, up to 15 volts is still a good choice. Okay, but anyways, so the purpose here is to show you how to get the pull-in analysis, which is very much important in a capacitive driven sensor devices. Okay, so here once the analysis is completed, for future use, future references, if we want to save the result file, there's a procedure to do it. So you have to save the result file. If you just save it here, project file without the results will get saved. Okay, so please save the result file here. So I'll give the name pull-in and whatever the name that you wish to give. So here the result file is being saved. Once the analysis file, the result file is saved, we can exit the module by cleanup and exit. It's always good to have this practice because it will remove all the temporary files that we generated during the simulation. When we exit the module and later we wish to get the results, so we can go to results and then open result file. So we can access this. Here we need to give a command, shift A, that is caps A, and then press enter. That will open the result file. The file is open. We can directly go to results and then we can see the results directly. Plots can also be extracted. Okay, so this is how we can open up a result file. So this simulation, whatever we have carried out, has given us the natural frequency value, and then it's given us the pull-in plots, and then the sensitivity analysis is carried out. So in microphone or in any MEMS devices, we always have something called as a squeezed film damping. This microphone being a acoustic pressure device, so sensitive device, so naturally we'll have to look for the viscous damping and thermal noise, squeeze film damping basically, okay, which has not been accounted in this simulation. So to incorporate all of those things, we will have to do a macro model simulation. So this is essential because these damping factors are driven by the ambient conditions. Based on the ambient conditions, the damping gets decided. The squeeze film damping, viscous damping, thermal noise kind of stuff. So naturally we'll have to do that. So for that reason, we'll have to do a macro model simulation. So let's do it. Let's perform a macro model simulation here. Okay, so here this is a quite a long running simulation. It's a sequence of 4 simulations that we do. Naturally, it will take a long time. So here we'll start with the model contribution. Generally, it is recommended to use 100 number of iterations for such macro model simulations, but in the interest of time, I'm using only 10. But however, even this 4 simulations that we do, the model contribution, strain energy versus model amplitudes, and mutual capacitance versus model amplitudes, and fluid damping coefficients. Almost every simulation takes quite long time. Okay, so here I just click apply and OK, and then we define for the vibrating element. When we select this vibrating element, which is the bottom, and enter value 3, we get this damping factor. So we'll consider this as damping factor just for the for instance. Okay, and then now we'll apply a voltage. So anyways, the voltage is applied somewhere, so it can go to below 5, or less than 10 is also okay. Anything less than the pull-in voltage, okay. It can be 5, it can be 6, 7, no problem. And the other value is anyway 0. Boundaries are fixed, and then we do the meshes are already done earlier. So we start with the macro model extraction. So once we do the macro model extraction, it runs the simulation for quite some time, and then we get the results. So what is the result that we get? So we get model contribution. Okay. So in model contribution, we see something. So what is this model contribution? So here we have what is the maximum contribution that's coming up, somewhere around minus 0.1. Okay. So this value, what we see, the other values will be shown as enabled. So if we double click here, it switches between disabled and enabled. So it has to be in the disabled mode. So you can double click on these two options, so you can disable the lowest values. So here we have the model contribution. So what is the model contribution here? In this case, it is minus 0.096. So we can consider it to be 0.1. So this value, whatever we have, we feed in here 0.1, and then we click apply, and then we say OK, and then just go to analysis and start macro model simulation again. Okay, so this will also run for quite some time, and then we get the result. I've already done those simulations earlier, so I'm able to open the results directly. So here we have three options in mode 1. So other two we had disabled it. So here we double click on this and then click OK. It turns enabled, and plot option also gets enabled, and then we click OK. So we get the strain energy associated with each modes of vibration. So this plot we get. Okay, and then we don't take this, there's not much we do further, and directly we go to mutual capacitance versus model amplitudes, and then we click apply. Okay, and there we directly go to analysis, and then again run the macro model simulation. So now once that is done, we again go to macro model and then click on mutual capacitance versus model amplitudes. So we get this, and then we double click, and again double click OK. So we get scaling factor versus capacitance. Okay, so the mode scaling factor, so somewhere around 0.1 is what we have. See, the boundary element method is adopted here, BEM. Okay, and then we close this. Now we'll have to say what is the fluid below it. So the fluid damping characteristics have to be defined. So we select this fluid damping coefficient and then go to squeezed film, moving phase. So which is the moving phase here? Moving phase is the top surface. So that is that green entity which is below is the moving phase. Okay, so that is selected. I think I close and I reselect it again so that it turns red. Yeah, it got selected. So I click OK and then go to boundaries, squeezed film, fixed phase. Which is the fixed phase? So this bottom phase is the fixed phase. So the bottom phase is the fixed phase. Okay, I click OK on this one. And now I go to boundary, complete pair. So in complete pair, I have to enable this by double click. It gets enabled, and then what is the viscosity of the ambient condition there? So here if we consider air, so we'll use this value 0.001 and ambient pressure. So this is the ambient pressure that I'm trying to feed in, and then click apply and then click OK. So further these settings are done, and then one more important thing is micro model representative nodes. So we select one center node here. So this is a very much important. So I click OK. So this is the node of interest because that is the place where we see the maximum displacement. So that's why we want to create that. So here I have selected, when I select the point here, so it turns out red. So somewhere in this region you can also plan to do the selection. So any one of the node which gives maximum displacement. So all set. So next we'll run the simulation. So once we click on this start macro model simulation, this will take very long time to complete this simulation. So here we click on this value. So we get this window. So we feed in these values, start frequency, end frequency, and number of frequencies. So these are the things, and then we click OK to this. So this runs the simulation. So once these 4 simulations are done, what we get is the 3 files. Okay, so here in the location where we are trying to do the simulation, in this location there will be 3 files. So these are the 3 files that we need to look for: corr.macromodel, str.out, macromodel.out. So these 3 files will be generated in the location where the simulation is done. So we copy this and then we paste it in a location. Okay, so we paste it here. So the 3 files is taken out. Now at this point we can close thermoelectromechanical module. Okay, so these 3 files. So before you exit thermoelectromechanical, make sure you copy them, because later you don't get the access to those files. So it will all be wiped off. So now what are we trying to do? So these 3 files are copied. What does these 3 files contain? So this is the reduced order model file of our microphone example. And then we have this file which contains the node of interest, the representative node that we selected. And then this contains the boundary conditions and the voltage that we applied. Once all those simulations are complete, so we open up a simple module and then go to macro model, select this macro model element. Then we go to sources, electrical elements, sources, voltage DC source. I can rotate this here and then I connect the positive here. I take the ground. So wherever we require an output, so we take this signal output and then place it here. So this is, since this is more in the Z direction, we connect it to Z1, the pin. Now let's go to source. So general sources, not electrical source, general elements. In general elements, we find sources, general AC source. We are applying the force in Z direction. So naturally, we have to connect this to Z, FZ1, force in Z. Double click. The amplitude that we need to give is the acoustic pressure. So we know that it is pressure is force per unit area. So we are directly converting it. So our dimension of the plate is 1000 micrometers by 1000 micrometers. So if we use P is equal to F by A, force per unit area, then we can get that 1 Pascal is equal to 0.1 micronewton of force. And we give a frequency range somewhere 1 kilohertz. Okay. And the other points, other inputs are all kept constant. Other inputs are all held constant. So we connect. We select this macro model template. We say, first we save the file. Let's save the file. Simple. So save the file. We select this ROM model, go to tools, load ROM macro model. So we have saved those 3 files. So we in the same in a folder. So we select this corr.macro model and then click OK. Then click yes. And we get this. Of course, 3D simulations are not possible with macro model simulation. That's the warning that it gives. And then we select, double click, and then if we want fluid flag is in case if the software while simulating the macro model, if the software needs to consider the fluid damping or no. If it is 0, then it won't consider. If it is 1, then it will consider. So let's consider it. And then we go to Qmax 1. So this is the model contribution. So we have 0.1 is the model contribution value. So these are the 2 major changes that we do, and then we click OK to this. We have applied a bias voltage of 5 volts. We retain that. And anyways, this is already set 0.1 micrometers. We save this file, go to analysis, then frequency sweep, a linear sweep we will do. 1 kilohertz. So we'll keep it to 50 kilo, up to 50 kilohertz. We will try to simulate, and then 1000 number of points. Then we click or go to signals. So which are all the signals that we require? So by default, N2 gets selected, meaning at Z point, what is the resonance value? So now this black box, this template is basically a FEM model. Okay. Now we click OK. Yeah, this is simulation is done. We will see. You can see that the response is somewhere around 38 kilohertz, 36 kilohertz. Yeah. So I think it's fairly closer. Okay. So here we have a matching results of micro model and then the FEM. So you can take this on the Excel sheet and then compare the TEM data with, so you can get large number of data here. So to perform the same on thermoelectromechanical, it's extremely difficult. So here we have 1000 number of points. So similarly on the log scale, it can also be plotted. You can run the simulation on the log scale as well. Okay, so you click OK and then you can run the simulation. So this gives us an idea of what macromodel simulation is. And now we have considered with no damping case. Okay. Just terminated the simulation. You can disable this and you can see the result. So you can disable fluid flag. Should we consider it or not? So when we compare both of them, we can plot the data. Okay. So this is how we can do a macro model simulation.